Okay, I think we'll get started. So we're in this stretch of the course here now. Maybe you saw the last video where it doesn't work as well for the Gian Lewis project, but I do have some videos from another course, and we'll be splicing those in here for the next couple of lectures. The key idea here is that a few things will be out of order. And in fact, in this inelastic collision, we're actually going to get a video on all the collisions. So we'll have this, this video will work for this topic, and then a couple of topics a couple of lectures down the road. So we're going to do this topic, we're going to get to angular momentum, we're going to get to energy, and then we're going to come back to collisions. This video goes through both of those collisions. So I'll bring us back again when we come back to that. So just keep in mind that the latter part of this current video, you can just maybe stop watching and we'll come back to it in a couple of days, or you can watch it just to get a feel for what's ahead. Okay, it will also involve some concepts of energy, which as we're going through in our path, we haven't quite done yet. Right, Concordia students, again, in-class work will be what we're doing, but you might find this useful. Just keep in mind that things will be coming out of the blue that we haven't talked about yet. Okay, I think we'll get started. So today we're going to talk about collisions. There's two extremes to collisions. One in which the particle undergoes what's called an elastic collision, in which no energy is lost to the event. So we just collide and come back out. So energy is conserved in an elastic collision. And then the other extreme is an inelastic collision. So this would be like a marble hitting a stainless steel wall. That, by and large, that's very close to an elastic collision. Any real collision isn't going to be perfectly elastic. The other extreme is inelastic, and this would be like a wad of clay hitting that stainless steel wall. And again, nothing's going to be perfectly inelastic, but a wad of clay hitting the wall will be pretty close. So there, energy is lost and transferred to the system. Now, if we have a single system, not a wall here now, but just say two particles, let's make it the simplest system that we can and still have a collision. Let's talk about inelastic collisions first. During an inelastic collision, momentum is conserved for the whole system. Energy is not, and how it's not is that we're not violating conservation of energy, but what's happening is during the collision, because we're sticking together, we're causing vibrations within the object, and it's effectively heating up the object, and we lose that to heat. Also, any sound, although sound doesn't carry a ton of energy, most of it's lost as heat in the collision. So we need only conservation of momentum to calculate these problems. So let's work through that. Say we have two particles, and we'll stay in one dimension first. Take two particles, and they're moving along such that one particle will collide with the other. So let's say this guy's moving this way. Could be any way, but say this guy's moving and this guy comes in and collides. Now we won't bounce off. We'll collide and stick. So this would be a good example here in chemistry would be if you have a reaction in which two molecules come together and bond and then go off as a single unit. The total initial momentum will be the momenta of the individual pieces, and the final momentum will be 1 unit. So we think of this as 1 unit. So this will be mass 1 plus mass 2 times its final velocity. Now, because of conservation of momentum, delta P is 0. So if we subtract this from this, in this equation, we get 0 equals that, and we can solve some problems. So let's take an example. Say we've got a 2 kilogram mass, a 1 kilogram mass. They collide and stick together. The 2 kilogram mass is moving at 5 meters per second. The 1 kilogram mass is moving at 3 meters per second. Let's calculate the final velocity of the unit that's stuck together. so m1 plus m2 times the final velocity, we don't know this, that's what we're going to solve for, minus 2 times 5 minus 1 times 3, well, that gives us 3 v final equals 13, or v final equals 13 thirds meters per second. Now, let's check to see if energy is conserved. And we said it isn't in an inelastic collision. So let's just calculate the kinetic energy of these before and after the collision. So we use 1/2 mv squared, kinetic energy formula. And so initial, we have the kinetic energy of 1 plus the kinetic energy of 2. That gives us our total kinetic energy. That works out to be 29.5 joules. And then we take the kinetic energy of the final unit, works out to be 28.1 joules. So we indeed lose a little bit of energy. Energy is lost. We have less energy after than before. All right, well, let's take this to 2 dimensions. It's straightforward. We just have to do our trigonometry now. So let's take this same system, but now this guy, this one that's chasing this one, is coming in at a 30-degree angle. They hit and they'll stick together. And if we think about it, this is coming in like this. They're going to hit and they're going to go in some downward direction. This one's moving this way, this way. Probably not the same as this, but something in between. So we can calculate the component-wise, the x and y component for the incoming particle using cosine of 30 and sine of 30 for x and y respectively. And then this one happens to be moving only in the x direction. So we can get its py right away is 0, and then its px is just mass times velocity. The final unit, well, we don't know these, but we do know that individually we need to conserve momentum. So we conserve momentum component-wise, and so this gives us a way to calculate very similarly to the one-dimensional, basically turn it into 2 one-dimensional problems, and we're able to get the velocity in the x direction and the velocity in the y direction. To get the final momentum, we could multiply by the total mass, and we get this vector here. I think I got that's a minus 5. So we're going down. So our momentum vector has a slope of over 11, down 5 for that. So these problems can come in all sorts of different ways. You might know the final momentum and have to calculate initial momentum. You might have to calculate masses. But basically, it's this same idea. We're using conservation of momentum to solve these problems. And we couldn't solve these problems in general if conservation of momentum didn't work. All right, let's turn our attention to elastic collisions. Now, elastic collisions, we said energy is conserved in an elastic collision. So we assume there's no transfer of, well, there's a transfer of energy, but none of that is transferred to the internal workings of the molecule or object. So if 2 steel ball bearings collide, we don't, yes, technically there are some vibrations and there's some sound, so we do lose some energy, but in the idealized case, we don't lose any energy. So we can utilize both conservation of momentum and conservation of energy. And so we have these 2 equations. We know the formulas for momentum and for kinetic energy. We could work out, it's a bit tedious, so we won't work it out. We'll just write out the solutions. So if you plug in all of the equations, so K equals 1/2 mv squared and P equals mv into all of those, and then solve for the final velocities of 1 and 2. And this is a one-dimensional problem again. It would expand by component-wise to 2 or more dimensions, but it's complicated enough in 1 dimension, so we'll just leave it as that. And so we get this formula. Notice there's some symmetry here. we have difference in masses over total mass. Total mass is in the denominator everywhere. We have 1 minus 2 over here and 2 minus 1 over here. And then the cross terms here are 2 times m2 and 2 times m1. So there's a bit of symmetry that works out, as we might expect, because we're just labeling one mass and another mass. So that's the general expression. Perhaps you could practice and just pretend this was not now an inelastic. They didn't stick together, but they had an elastic collision. See if you can work out the final velocities. Now what we're going to do is look at some cases of these. So I think I'll erase the board here and focus in on these cases. So let's look at case 1, which is when the second mass is sitting still. Use a little bit darker. Well, in this situation, V2 initial is 0. And so these terms cancel. And we get that. And so the components are given to us by the initial, or the final velocities are given to us by the initial velocity. This is one initial of just the incoming velocity. Now we do see that the final velocity, as we might expect, when this hits, boom, this will bounce off. The final velocity is not 0, so it's going to move away as we would expect. All right, let's look at this under the special case of case 2. So now we're going to get these terms to cancel here. And so that's interesting. So V1 final only depends on V2 initial and vice versa. And so they sort of exchange velocities in a weighted way, a mass weighted way. So let's let's combine these two cases here now. Case 3, let's take that as case 1 plus case 2. So case 1 plus case 2. So from case 2 we have this, and now we have V2 initial equals 0. So V1 final equals 0. And V2 final equals 2 mass 1, M1, M2, V1. So that's kind of an interesting case there. So if V2 is sitting still, and then this mass comes in, we will... Oh, I shouldn't have 2's here. Yeah, these are just... They will just exchange velocities. And case 2 says they'll exchange velocities. This is an interesting case where the initial case is 0. So this will come in, hit, and go. Hit and go. Okay. Great. And let's do case 4, which is also interesting. This is when M2 is much, much less than M1. So like a freight train and a ping pong ball. So V1 final is then approximately equal to, well, compared to M1, M2 is going to be essentially nothing. So we will get M1 over M1, which will cancel V1 initial. And then this will be essentially 0 because we'll have M2 very, very small over M1, which is very big. V1 initial. And then V2 final. This will be 2M1 over M1, basically. V1 initial. Well, this will be minus M1 over M1. V2 initial. So this is approximately equal to 2 V1 initial minus V2 initial. So let's look at this. If this freight train is coming and we throw a ping pong ball at it, well, the final velocity of that freight train is not going to change, right? It'll just keep going at the same speed. This is let's see. Let's do 2 cases here now. So let's imagine that freight train going very, very slowly. We throw a ping pong ball. That should behave very much like a ping pong ball we throw against the wall. And if the freight train is going very slowly, such that this is basically 0, which a wall would be. So a wall, you could think of that as the freight train has come to a stop. So huge mass, but velocity is 0. Then we just get a rebound, an elastic rebound of minus the incoming initial velocity of that ping pong ball. Now this is a little, then let's take the other case where the ping pong ball is sitting still and the freight train comes and hits it. So the freight train comes and hits it. Maybe a little counterintuitive, although you kind of think that if the freight train hits it, it will bounce off, right? So this is sitting still. So it won't necessarily do that, but it'll do this. And so then the velocity that this takes off with is twice the velocity it got hit by. So if it gets hit by something very big, then it'll take off, it'll bounce off of that with the velocity twice that. So looking at some of the limiting cases of this is pretty interesting, and it helps us develop an intuition about the general case. And so as we think about molecules, we can often think about either an elastic collision in which there's a bond that forms and they go off together, or an inelastic collision where they bounce off of each other, conserving the total energy. Now, getting into more of the details, if we have, and we know molecules have geometry, so we might hit and impart a spin, some kind of angular rotation, and that then gets more complicated. And so we would have to worry about some of the internal dynamics, or a vibration. We might initiate a vibration in the molecule. And so that can get pretty complicated. But we can think about a lot of the kinetic behavior of chemistry just based on this simple collision. And we will in second or third introductory course, we'll talk about simple collision theory for chemistry.